Today we're going to take a look at this little tiny Tamagawa motor. It's got incremental encoder with Halls, but it's got a wire saving. Today I'm just going to set it up with incremental encoder until I get the firmware and features for the wire saving. We've got it for the Sanyo, but there's a little tweak for the Tamagawa. Anyways, this motor is very interesting. Besides being very small and narrow, it's a little coggy. So we're going to see how to try to reduce the cog, the pole-based cog in this motor. So we'll take a look at that today. So here are the dimensions, the mechanical outline for this little motor. Looks like 22 millimeters for the front plate. There's cabling, the motor power, red, white, black, and an earth for UVW. We've got +5 and ground for VCC and ground on the black and red. And the blue and blue-black is A naught, green, green, black, B naught, ZZ naught for yellow, yellow, black. But they also pose a U, V, and W differential for commutation. So on power up, we can look at the position and then switch over to the encoder-based sinusoidal. So that's the basic wiring for the motor, and we can see the encoder 2050 is 2,000 counts per turn. That's a line count. It's actually 8,000 pulses per rev, or 2,000 line, 8,000 counts per rev. And we have the motor specification. Interesting to note, the amps RMS is 3.6. So the Newton meters per amp is the units of RMS. They didn't specify that, but that's just the way the math works out. And it's got low volts per kRPM. I just entered the Newton meter per amp in for volt per radians per second and converted over to volts per kRPM right in CME2. So we've got the peak torque and the stall or rated torque, and the speed of the motor is indicated around 5,000 RPM with 24 volts intermittent duty, continuous duty. But this thing could actually hit 8,000 RPM with the incremental encoder. So we'll just set it up for safety limits there. So I'm not going to go through the basic setup because we don't have the wire saving in there yet. I've got it configured at the moment for just incremental encoder, wake and wiggle, but with the wire saving, we can do the Halls and incremental encoder. But basically, enter the motor data, 8,000 counts. We can enable the loss detection. That's no problem. So the first thing we do after checking out that we've got some current loop is that we can take a look at the phasing of the motor. So because this is in relationship to the cogginess of the motor, it's good to investigate phasing. So I'm going to just give it an amp of current vector. It's pointing towards the 0 phase angle of the electrical cycle, and I've got 1 count. I can set that to 0. If I turn the motor shaft by hand, I can feel 1, 2, 3, 4 positions that the motor shaft can be in. So it's an 8-pole motor. We can also see the count has hit approximately 8,000 counts per rev, plus or minus a little bit. It's just a current vector open loop microstepping. We can also set the phase init current. I'm just saying there's only incremental encoder now, but there's actually Halls. But we can ramp up with 1 amp of current to do the algorithmic phasing to phase the motor. That's phased. Part of the manual phasing is to give it a rotation, so that's why it's spun. So good no-load thing to do. But you can see we've got 8-pole. That's something they did not indicate in the data. And we've got 8,000 counts per rev. And that was confirmed on the manual phasing screen. So just the basic calculated tuning was pretty soft, but I'm going to show the effect of the cog when we make a move here. So given some pretty basic tuning, kind of soft and spongy, and the default filter pole of the V-loop at 200 Hertz, we can see a slow single rev move, and you can see all the cog based on this trajectory. About 8 times per rev. If we double the speed, you can see the cog will be based on the 1 rev of the motor. As the speed goes up, the frequency increases. So it's just an inherent cog. As you go faster, your inertia tends to smooth things out. So the cog gets relatively smaller as you go faster. But another way to improve the cog is just by having some good gains and good tuning. If we move the pole out, make it a single pole, this will allow us to increase the gain here. And we can see it change from plus or minus 40 counts down to plus or minus less than 20. A little stiffer position loop here. It's not a complete procedure for tuning, it's just indicating that the gains can help squish down any disturbance that gets injected into the system. So this is an inherent cog in the motor, and the best we can do is try to reduce its effect by increasing the gain. And this was approximately the highest gain that I wanted to do for typical moves. And again, its relative amplitude is, plus or minus maybe 6 counts. And a little more velocity loop bandwidth gives us the ability to squash the disturbance per rev. As we go faster, the frequency of the disturbance increases, and we might see the error go up. But then again, the inertia helps bring the error down. So when we hit some higher speeds, the amount of error is insignificant. So we can see still when the speeds are lower, the frequency is larger amplitude, and then as speed reaches a certain point, the relative cog disturbance is reduced just by the inertia. So that's the same thing during deceleration. You can see at a certain speed, less than 1,000 RPM, the cog becomes apparent. This does not affect the tuning and settling so much. We can turn the integrator down to get it to settle a little more well-behaved. So yeah, it's interesting. The fan acts with a little bit of a load on that. So for minimizing the settling time, plus or minus a count at the end of the move, even though we have a little bit of cog when we're going slow, This did not affect the overshoot after the move is done. We got a pretty good stable move and settle, plus or minus account, and I'm just quieting down the ring a little bit here. This is a well-tuned servo loop, so this is probably not necessary to do this. There'll be a load inertia on it, and that will also reduce the ring on it. And of course, this little bit of a ring at the end of the move is either at the current loop or velocity loop pole. So there's a normal settle plus or minus account, very stiff tuning, and sufficient gain and inertia to reduce the cog ripple, especially at velocity. So at 3,000 RPM, our following errors plus or minus a couple of counts. So the integrator helps bring us in, and the feed forward term reduces the error to 0 while we're moving. Okay, well, thanks for watching and learning about cogging effect based on the motor pole count and speed. We see a variation in frequency based on the speed of the motor and not at a specific mechanical resonance in the system. So this is speed dependent vibration due to motor cog ripple. Thanks for watching.